our first part of the workflow where we established our base rock. So let me just rearrange things a little bit. And we can also create a network box with this button here, so we can keep things organized. Now for the next part, we are going to subtract pieces from this rock, so we can basically simulate the breaking up of the shape over the years. In order to do that, I want to remesh this shape first because it's too wide for a scattering operation. So let's drop down an object merge, and let's take this base rock as an input. Also, I want to mark this as green, so I know that it's linked to one of my main outputs. And we're going to drop down a BDB from Polygon. If you're not familiar with the BDB, they are basically an open library. They are used to compute volumetric data, also in a sparse way. So if you work with volume or VFX in general, you will see those a lot. But since they are very light to compute, they are super useful even for modeling operation. The way they work, they basically convert your mesh into voxels. So you have a 3D data as a volume. We can lower the density by changing the voxel side. And for this one, we want a pretty big size, so let's say 0.4, and we want a surface VDB. You can also create fog VDB if you prefer, but in this case, we just want the distance. And if you go inside, it's not a filled volume because fill interior is unchecked. So this is pretty fine for us. Now let's take the VDB smooth, so we can smooth things a little bit. Oh, sorry, not this one. We want the VDB smooth SDF. So let's plug it to the VDB from polygons. I believe it's fine. And now we can convert this VDB back to polygons. So let's plug a convert VDB to our smooth and change the convert to polygons. So now we have polygons back. It's a super light mesh and it's perfect for my scattering operation. Now we just want to drop down on normal to fix any visual issue. And we want the normal assigned to the points. So let's rearrange these things and drop down a null. We want to make it green and call it out scatter. So now we can create another object merge. This time I want the out scatter mesh to be my input. Let's make it green also. Set green. And we take a sphere and we can drop down our scatter, plug the object merge into the scatter. Let's make it like 10 points for now. And we can copy 2 points to sphere. Let's make the radius 1. And this is the core concept of it. Now we have to make a lot of work in the middle. So the first thing to fix is that right now the scattering is happening on the whole mesh. And I don't want it. We want to establish some density value so the rocks will not be scattered on the bottom and on the top of our mesh. So let's drop down a point wrangle where we will compute our density. Let's call it density. And let's establish some initial value so we can go inside the scatter and activate the density. Otherwise, without a base value, we just get an error. So let's and put the display flag on the density, so we're going to see what we're creating. In here, let's create a float variable called density, and we will use a ramp to drive it. So chramp, let's also call the ramp density, and it will be driven by the position y. Let's replace this one with the new density value we created and click here to create this pair parameter. Also, we want to go into edit parameter interface because we want this density ramp to be a color type. Apply and accept. Let's change one and color. And over the point wrangle, let's click on the eye and click on the density attribute to create a visualizer for it. As you can see right now, it's not working properly because, as before, the ramp is expecting values from 0 to 1 and our rock is 4.2 tall. To remap those values, we want to create a couple of vector variable. The first one will be called min, and we will use a function called get bboxmin from the first input. Basically, we are creating a vector variable, and we are asking for the minimum bounding box value coming from the input number 0, which is the first one. So here we will have 0 because our mesh is touching the ground, and we want to create a second variable called max, and we will use another function called get bbox max. So this attribute will be outputted as the current maximum height, meaning 4.2. Basically, we can use these two variables to remap our ramp. So let's use a fit before the ramp. Oh, sorry, not before the ramp. We want to just fit the position. So fit before the position. And the position will be fit between the minimum value and the maximum value as a source. And for the destination, we just want 0 and 1. We get a warning here because vector to float. Oh yeah, because we're using vector variable to remap a float variable. So in here, the min and max value, you can just add point y. So we are asking for the second component of this vector variable. Now we don't have the warning, we have a correct density value that we can remap by editing the ramp. So we say we don't want to scatter on the bottom and also on the top, so we want to have something like this. And of course we are going to tweak it later, but the base idea is this one. So back on the copy to points, let's get rid of this visualizer. You can see that by editing the ramp, we are confining the scattering effect only on certain height of our rock. Next, we want to randomly offset some points because as it is right now, they are all exactly on the surface of our incoming scattering mesh. So to randomize those a little bit, we will use a point bob and we will plug it after the scattering. Let's call it this place and go inside. In here, we will use a turbulent noise, connect the position to the position of the noise, and like before, we are going to use this to drive the amount of displays along normal node. So plug the position and the normal into the displays along normal and output the position. So now we can set this noise to be, let me just go back outside for a second and put the display flag on the copy to points. Let's turn off this also and go back inside. Now let's put a height frequency, something like 7.5. And let's also plug a fit range to the amount in case we want to edit later. We can promote the destination minimum and maximum. And for the incoming value, since we are using an alligator noise, This is going from 0 to 0.4, I believe. So as you can see, it's not that much. This is just to add some little variation. You will see that inside a complex setup, a lot of these little things will really help you to make your scene seems more natural, and it will not look weird to the eyes of a viewer. Next, we want, of course, to work on the scaling of these spheres, because right now they are all the same. This time we don't want to use the p-scale value, because we want to be able to have different value for the x, y, and z scale. Luckily for us, the copy to point recognized by default another value, which is called scale, and it's a vector value, so we can have different value for the different scaling component. So let's drop down a point wrangle after the displays. We will call this scale, and inside let's create 3 float variables. The first will be called scale x, it will be equal to 1, and another 2 for the scale y and the scale z. So now we can combine those values in a vector variable. We will call it scale. It will be equal to scale x, scale y, and scale z. And we can put all of this inside an attribute. So at scale is equal to scale. Now if we change those numbers, let's say 0.2 for the scale x, 0.5 for the scale y, and 1 for the scale z, you can see that we are working on the separate values for our scaling factor. Now for the values, I want the z-scale, I want to leave the z-scale as 1, because it's the axis that is going inside the shape, and we want to be sure to carve enough of this rock. Also, we have the variation for the z-scale here, because we are moving outside the copy itself. So we want to add the random value for the x and y axis. Before doing that, let's create a float variable, call it seed. We will use it to change the overall seed of our values for the scaling. So let's create a CHF, let's call it run seed, and create this parameter. Now for the x and y, we want to use a rand function. So rand, that will be based on the point number plus some random value plus our created seed. And we want to do the same for the y-axis, but we will change the arbitrary number. So let's say 6 for 3. Now we randomize the x and y scaling from 0 to 1. If you remember, the random function will give you a value from 0 to 1. So we want to fit this range with a fit 0, 1 function. And we want to use a newly created parameter. We will call it CHF min x, and another one called CHF max x. Create the spare parameter, and now we can remap the minimum and maximum value for the x-axis. So let's do it the same for the y-axis. So CHF min y and CHF max y. So now let's say I want the max and min y going from 1 to 3 and the x from 1 to 2. And of course we have complete control over the seed. So we are scaling the x and y axis, but not the z. Now we can edit the density ramp a little bit. Let's say also display the scattering mesh. Let's say I'm fine with something like this for now. Lastly, before moving on the shape of the sphere itself, I actually want to edit the rotation of the copies, but I don't want to randomly rotate each copy on all axes. I want to rotate this along the up vector. If you may recall, when we do a copy operation, the normal of the point is deciding the orientation of the copy, and with the up vector, you actually decide the rotation along these normals. So in order to randomize only the up vector, we are going to use something called the quaternions. So basically quaternion, at least in Houdini, are expressed as vector 4, meaning they are vector with 4 value. You have x, y, z, and you have also a w value. And you will mostly use those to express rotational transformation, because let's say this second way to express quaternion in Houdini, you will be asked for an axis of rotation and for an angle, meaning how much you want to rotate this quaternion. Basically, let's say we have our scattering points. We will use 3 of the 4 values available in a quaternion to define our rotational axis, that in this case will be our normal, and we will use the 4th value to define how much we want to rotate this copy or along the normal. And then we can use, if you recall, you have an up vector defining the orientation of each copy. We can use the quaternion to rotate the up vector itself, resulting in a random rotation, but only along the normal of the copies. So in practice, let's drop down a point wrangle. After the scale, let's call it rotate. And inside, for the time being, let's create a t angle variable, which will be temporary. We are not going to use this as a final result, and it will be a CHF. Let's call it t angle also for the name, and semicolon, and click here to create this pair parameter. So right now it's going from 0 to 1. We want this to be from 0 to 360. So let's change it in the maximum range, apply and accept. It's going from 0 to 360, okay. Now let's create our quaternion, so vector 4. We will call this quaternion rotate, and we said we want to use this form to express it, because we already have the axis, we just created the angle, so we are good to go. So quaternion, it will be t angle and our normal. Now we actually need to use the quaternion to perform a rotation, and you will use this function qRotate, where you will be asked for a quaternion and a vector. We said we want to rotate the up vector, but we didn't define the up vector yet, so let's do it right now. Before the quaternion, let's create a regular vector called up, and let's set it to be 1 on the y-axis. Now we can actually perform the rotation on the up vector. So let's write qRotate. We need to express a quaternion, that is rotate, and the vector we want to rotate on, so the up vector we just created. Now if we change the t angle value, you can see that it's rotating the correct way, but is going crazy. That is because the angle you are asked inside the quaternion, it needs to be expressed in radians. So if an angle in degrees goes from 0 to 360, the equivalent in radians will go from 0 to 2 pi. Luckily for us, Houdini has a radians converting function, so radians, and you give him inside the angle expressed in degree. So now from 0 to 360, you just do one single rotation. So this is fine, but we don't want to express the rotation with a channel. We want to express it in a random way. So let's create another angle value, float, angle, it will be our definitive one. And we said random, so let's use a random function over the point number plus some arbitrary number. So now we have a value going from 0 to 1. Now we can either remap first this value with a fit node from 0 to 360 and then use the radians function. But there's a better way, because we can multiply this value going from 0 to 1 by pi itself. So now we have a value from 0 to pi. We say the radians angle going from 0 to 360 will be from 0 to 2 pi. So we just need to multiply this value by 2. Now we can replace this with the angle variable, and we have the copy rotated in a random way going from 0 to a full rotation. So now we can delete this t-angle variable, and also in the edit parameter interface we can delete it here as well. So apply and accept. So that's it for the scattering points. Now we need to take care of the copies itself, and maybe let's find a better seed value for the scattering itself. Alright, so let's say this is fine for the time being. Now let's go on the sphere, and I want this to be to polygon type with a very high amount of polygon, let's say 80. Next, drop down a mountain node after it, so we can start to add some noises. And I want to use this Worley cellular because it's already giving me a rocky feeling, which I like. Now we can increase the amplitude to 0.6, and I want this to be only in the positive axis. Maybe we can set the element size to 1.2. As for the noise parameter, I believe it's fine for now. And then we want to add another noise, this time with a point bop. So let's call it noise and go inside. In here, we will drop down a couple of turbulent noise. So let's plug the position. And we want to use the original Perlin set as 3D noise for the first one, and we will add it to the current point position. So plug the position and the result of the noise, and we also want to fit range the noise, because original Perlin, as we said before, is going from negative to positive, so it's roughly from 0.5 to 0.5, and we want to remap it to a full range of -1 to 1. On the noise itself, let's lower the frequency, also lower the amplitude a lot, put it something like 1.3. And I want to duplicate this noise. For the second one, let's first add also this one so we can see the result. And for this second one, I want to use this sports convolution with a higher frequency, let's say 2.5, maybe offset also, so we don't have the same output as the previous noise. Lower even more the amplitude and maybe the roughness also. As for the fit, I believe it's fine. So if we go back on the copies, we have some noise pattern for the shape itself, and I believe it's fine for now. So I do like the shape of the sphere itself, but as you can see, we lost all the strata effect. If we subtract this from the main shape, we have a stratified effect where this is not going to happen, but on the curve portion we will have this kind of surface. So we want to add back some of that strata effect. We will do it with another point bop after the copy operation. So let's call it horizontal noise and dive inside. In here, just as before, we are going to add some noise to the current point position. This time we're going to use an anti-aliased noise. So let's plug the position and set it as a 3D noise and plug into the add node. For the noise, we want to increase the Y frequency by a lot, something like 12, and lower the amplitude by a lot. Let's say 1.4. So we immediately got some of that strata effect back. And we also want to use another noise, a turbulent one. Let's plug the position and plug it as a 3D noise on the add node. For this one, let's just lower the amplitude to something like 0.3. We don't want any major effect. We honestly don't care about fitting it. It's just to add some random values all over the shapes. So we have our mesh ready. So let's drop down a null, make it green as usual, and call it out subtract. So now we can do our subtract operation. Let's drop down a VDB from Polygon and plug it to our base rock. Now for this one we want a low value, so let's input 0.01 as the voxel size. So we have a nice height detail mesh. And let's copy the VDB from Polygon. We want to do the same thing for our subtract. And since we want to be sure to use the same voxel size for our operation, let's go on the VDB for the base rock, copy the voxel size, and paste relative reference here on the subtract. So now we can use a VDB SDF union to combine those shapes. So let's plug the base rock on the first input and the other rocks on the second one. By default, it's set as a SDF union. We want to do a SDF difference. So now we have our pieces subtracted from the base shape. Right now is too much, but let's put the display flag on the base rock for a second and the template flag on the subtract node. If we want less of this, besides edit all the parameters we created, we can just simply move the center of the sphere on the z-axis to make it less heavy on the subtraction operation. So let's say we put it to something like 1, so we have some curve but not too much. And let's go back on the VDB union. Yeah, I believe I will leave it as it is for now. Alright, so we are done with our subtract operation. Let's rearrange things a little bit and create a network box for this subtract operation. Just move the scattering setup up there. Now we're going to create the cracks that we want to subtract from the basic shape.